Okay. Um, so I want to break these videos up a little bit. The ones that I've tried to upload that are over a half an hour just take forever and have been crashing on me on occasion. So I figure if I keep, less video, well, more videos but less time, it'll, hopefully not mess up. Anyway, back to where we were. So here's the example that we're going to use. So we have white, black, Asian, and Latino. I guess I should put Latino, Latina. Perhaps Latinx would be better there, but I'll change that for you. Okay, so take a look here, and let's just see what this table tells us. Well, so we have a sample of 6 people who identify as white, 5 people identify as black, 6 identify as Asian, and 6 identify as Latino. So these are our sample sizes. We have 4 groups, and one thing to note, and I did throw this in there, your sample sizes don't have to be the same. So if you're comparing different groups, you don't have to have the same sample size for all of them. That's one thing that just keep a note of that. And then, so of these, let's say 6 people who identify as white, we look at, these are years of education. So 12, 12, 14, 12, 12, 16. If you think about what those really mean, this is probably, high school graduates at 12. 14 would be, a 2-year college degree, so an associate's, or junior college, something like that. 16 would be your kind of standard bachelor's degree. Obviously, and then we have variation. We see 20 over here. These are your, post graduate, so master's students, potentially PhD kinds of stuff. But anyway, so years of education, obviously this is an interval ratio variable. So I expanded this a little bit here. It's the exact same thing. I just added some numbers that we're going to need, and let's walk through what each of these are. So X bar 1, X bar 2, X bar 3, X bar 4. What are those? Well, X bar, remember, that's just the sample mean. So X bar for group 1, 2, 3, and 4. Now, you don't have to label these. I mean, we could have made Asian 1 or Asian 4. It doesn't matter where it is, but you will want to, subscript your means and your numbers moving forward, because you want to keep those organized. Now, you could also make it X bar W, X bar B, whatever you want to make, as long as you're being consistent. But you want to keep these numbers separate because these are the group means for these different groups. So you're just looking across, you can see that kind of the outlier here is that Asian seems to be much higher in terms of their mean years of education. So of these 6 people who identify as Asian, their average amount of education was 16.67 years compared to Latino, which is 12.5, Black at 13.6, and White at 13. So underneath, you'll notice that I have S1 and then S1 squared. Think back to what that is. Remember, S squared is your variance, and S is your standard deviation for the sample, right? And remember that I said that in order for us to do an ANOVA, the population variances have to be approximately equal. So I showed this to you because I want you to show what, I want you to know what approximately equal means. Now, if you look, the least amount of variation is within this group. The most amount of variation is within this group, and then the others fall in between. So I guess what I just want to emphasize is, are these variances approximately equal? Yeah, 2.28 and 4.28, they're close enough. You'll be violating this assumption if you had a variance of, like, say 15 and then 2. And what does that mean? This just means that there's less within group variation than there is here. There's more variation within this group than there is this one. That's what the standard deviation, that's what the variance is. But I just wanted to show you how this is an instance where, yeah, these variances are close enough that we satisfy the assumption. The only time you'd have to be worried about that is if you, like I said, if you got a variation or a variance that was, 4 or 5 times another one, then it's a problem. Even this it's not quite twice the amount, but it's close. But anything under twice the amount, you're fine to go. like I said, I'm not going to throw you any curveballs and give you any, try and mess you up on this assumption. But just know that in order to do this, the variances do need to be, relatively similar. And, they don't have to be the exact same. Obviously, these are, really, really close. But, yeah, these are close enough that we'll be okay with it. And then when you take the square root and you get the standard deviation, you see that they're even closer. There's really not much difference in terms of the variation across the group. So we're good to go. Okay? Whoop. Knocked my phone out of my hand. The last thing to note is that we have this x bar total, which is the total mean across the whole sample. So I also want to stress that here's the group mean for these different groups. We can't just add these 4 up and divide by 4. Why? Because the sample sizes are different. So in order to get this x bar total, we add up all of the years of education for everybody in the sample and divide by 23. 6, 6, 5, and 6 is 23. So you have 23 people across 4 groups. You can't just add up the group means and divide by 4 because the sample sizes are different. If you've ever heard a statistician say, you can't take the mean of means, this is what they're talking about. You could if these sample sizes were the same. If I made this group 6 as well, then you could do that. But I gave this to you so you can see that the proper way to calculate the total mean is to add up all of these years of education and divide by 23. Okay? I'm just going to say this one time that be careful with your calculations. It's really easy to mix these numbers up. Kind of the same as the chi-squared stuff. And again, the same as the hypothesis testing. Gotta write this stuff down. It really kills me when I don't see any work written out, and I don't know where I don't know where people are getting numbers from. Please write the equations down. It'll make your life so much easier. So keep organized. So like I said back, kind of early on in the first video, that the calculations for ANOVA have to do with 2 types of variance, between the groups and within the groups. So going back here, I said before, within the Asian group, there's more variance than there is within the black group or the white group, okay? But the point is that we're comparing the variation within each of these groups to the variation across the groups as represented by their group means. Okay? And that's really all it is. ANOVA is just a balance between, is there more variation between the groups or is there more variation within the groups? If there's more between, then we're going to say that we reject the null and we find that the groups are different. If there's more variance within than between, then we say the groups aren't different, it's just the composition of the groups have a lot of variance. So the differences are within the group, not so much between them. And then the estimates for the estimates for each of these variables between and within have 2 parts: the sum of squares and the degrees of freedom. Okay. So the first thing we get to, is the between group sum of squares. So take a look at this definition and think about what it means. The sum of the squared deviations between each sample mean to the overall mean. So here's the equation. Sum of squares between is equal to the sum of n sub k times x bar k minus x bar squared. And this is, it looks a little complicated, but it's all stuff you know. N sub k is just the number of cases in the sample. So think about what that is. The number of cases in a sample. K represents the number of different samples. So if we're thinking about our n sub k, how many cases are in the white group? Well, 6. How many cases are in the black group? 5. How many cases are in the Asian? 6 in the Latinx group too. So n sub k just indicates the number of cases in your group. The number of cases in your sample. X bar sub k is the mean of the sample, right? So we looked at the mean for the different groups. That's just your group mean minus the overall mean squared. So if you think about it, the sum of squares between can be understood as the amount of variation in the dependent variable, the years of education, that can be attributed to or directly explained by the independent variable. So the sum of squares between is going to give you an indication as to how different the variation is between the groups. So a high sum of squares between is going to, kind of indicate that, well, these groups are different. A lower sum of squares between is going to, kind of lead you to think that they're not so different. They're, the differences between the groups isn't that great. The within sum of squares, the within sum of squares is the sum of the squared deviations within the groups calculated between each individual score and the sample. So this is the variation within the group. So within white, within Latino. So the n sub k is the same thing. It's the number of cases in a sample. X sub I squared are the squared scores from each sample. And in the equation, we take the sum of the squared scores from each sample. So you're going to take each of the scores in the sample, square them, and add them up. And then the sum of the x sub k are the sum of the scores from each sample. So that's the sum of all the scores in the sample. Again, it's going to make a lot more sense when we get to the actual numbers here in a sec. It's, I know that it always starts nebulous with the equations, but we'll get there. Hang with me. So the explained sum of the squares between and the unexplained sum of the squares within compose the amount of variation within the scores. So there's differences within the scores, and we're comparing how much of it is explained by race ethnicity. So if think big picture, there's variation with how much education people have. Why do some people have more education than less? There's a plethora of reasons. Think of any number of reasons why there might be differences in people's educational levels. But what we're testing to see is, in this case, are differences in education levels, can they be attributed to racial and ethnic differences or not? So basically, is race ethnicity an independent variable that predicts education or not? Obviously, there's others out there, and that's what is unexplained in our hypothesis. So all we can explain is the educational differences based on race ethnicity. All the other variation, all the other variance within the groups is driven by something else. So what we eventually want to land on is the total sum of squares. So that's the total variation in the scores. It's the sum of squares between and within. So all the variation can be attributed to between group variation and within group variation. Okay? So I told you that you need sum of squares between, sum of squares within, and the last thing you need is the degrees of freedom. The degrees of freedom is a little bit different here, so pay attention. Like I said, in order to estimate the between and within group variation, you need the degrees of freedom. The sum of squared between degrees of freedom are easy. It's just the number of samples minus 1. So in our case, we have, what's our K? It's 4. We have black, white, Latino, and Asian. K minus 1, 4 minus 1 is going to be 3. The sum of the squares within degrees of freedom is a little bit different. It's not hard, it's just different. Sum of the squares within degrees of freedom is calculated by taking the total number of cases minus the number of samples. So in our case, we had 23 people across 4 groups. So we've got 23 minus 4 is going to be, what's that, 19. Duh. Yeah, 19. Okay? And I'm going to work all this out for you, but just so you know, this is where it's coming from. Okay. Lastly, in order to compare and calculate our test statistic, we need to calculate the mean square between and the mean square within. The mean square between is simple. It's just the sum of squares between divided by the degrees of freedom between. And the mean square between is the sum of squares, the mean square. That's a typo. Let's change that. Mean square. Was it a typo or was I just speaking too quickly? Yeah, no, it is. Mean square within. Sorry about that. Okay, so mean square within is the sum of squares. Sorry, sum of squares within divided by, I thought I had this edited out, divided by its corresponding degrees of freedom. So the mean square within, sum of squares within divided by degrees of freedom within. So let me just outline what you're going to be doing here. So you've got group 1, group 2, group 3, group 4, okay? So you want to compare the sum of squares between to the sum of squares within, right? So the within is like, you know, within the group variance. The sum of squares, the between is the variation between. So it's like, you know, so basically, I mean, really all you're comparing is the between group variation and the within group variation. That's really all it comes down to. So the first thing you have to do is calculate the sum of squares between and the sum of squares within. Okay? Next, so you have to calculate this first, and then you'll calculate degrees of freedom between, degrees of freedom within, and then and then you'll have to get mean square between, mean square within. So you first calculate this, sum of squares, and then you get the degrees of freedom, which will allow you to calculate the mean square between and mean square within, which the mean square between is just the sum of squares between divided by the degrees of freedom between. But you can't get that until you have these two parts. So start here, step 1, step 2, step 3. So you get those mean square within, mean square between, and then you end up with an F statistic, which is equal to the mean square between, mean square within. So the F statistic is a test statistic calculated by the ratio, God, sorry about these typos, of mean square between to mean square within. And remember, the mean square between is equal to the sum of square between divided by the degrees of freedom between. So, let's go through it again. Calculate sum of square between, calculate sum of square within. Get degrees of freedom between, get degrees of freedom within. Then you, in order to calculate mean square between and mean square within, you just take. So mean square between is going to be sum of squares between divided by degrees of freedom between. Mean square within will be sum of squares within divided by degrees of freedom within. Right here. And your F statistic will just be the ratio of mean square between divided by the mean square of within. If it's larger, it's going to be above the critical value. Most likely you're going to reject the null. If it's smaller, it's going to be below the critical value, then you're going to fail to reject the null. And if you think about a big picture, what this really indicates is if you have a really large mean square between, let's say this is 20 and a mean square within of 2, well, you're going to get a pretty big number, say 10. I mean, these are just arbitrary numbers, but what it's saying is that most of the variation is between the groups. Within is a lot less. So you're going to get a high test statistic, you're going to reject the null, and you're going to say that one group is different. We found that it's like there is more variation in the between. Now, if you get a mean square between, let's say, of 2 and a mean square within of 10, flip it, and you're going to get 1/5 here. Well, that's really small because most of the variation is within. So again, you're just comparing between and within. Okay. So let's do our practice. I'm going to pause the video and start a new one, which will just be the practice.